Hey class, today we're taking a look at our second unit, which is algebra and polynomials, and taking a look at algebra expressions, and we're taking a look at if they're equivalent. So again, if you want to put a new title page or a marker in your book, this starts unit 2. So taking a look at warm-ups, ladies and gentlemen, again, this unit focuses mostly on algebra, so it's a different shift from unit 1, which was intro to functions. We're going to be first taking a look at some terminology. If you need to write these down, please feel free to do so, but many of them you might know on your head. So taking a look at what a term is. Okay, a product of a number and a variable with an exponent. Terms can be separated by adding and subtracting signs, as well as multiplication and division signs. Taking a look at this example right here, I'll just get my highlight out, ladies and gentlemen. So taking a look at this example right here, please note there's two terms, so we call that a binomial, and there are two terms within it, which is called 5x and -3, where 5x is the variable term and -3 is the constant term. Note that within 5x you can break those down into smaller bits, whereas 5 is the numerical coefficient or the coefficient. It's the number in front of x, and x is the variable. All right, taking a look at our second definition, a polynomial. A polynomial is an expression with one or more terms. Exponents are whole numbers and coefficients are real numbers. Okay, let's take a look a little bit more at that coefficient or numerical coefficient. It's the number which the variable is multiplied by. So in this example here, -4 is the coefficient. Okay, a constant term is a term with no variables. An example here above, the -3 is the constant term. There's no way it can be changed. So a constant term basically stays constant, whereas if you have a variable in it, you can substitute any variable in for, or any value in for that variable. So that's why you call it a variable term. A constant term, again, is a number all by itself. All right, so taking a look at today's lesson, we have 2.1, adding and subtracting polynomials. Basically, we're looking at the distributive law. So let's take a look here, ladies and gentlemen. Example 1 is to simplify. And just remember, guys, when you're taking a look at brackets, in order to collect like terms, you have to see what sign is in front of them. For example, the first sign in front of the bracket, there's nothing there, so that's understood as a positive sign. When it's positive, you can simply drop the brackets. Same with the second example. But the third one is tricky. There's a negative in front, which means, hey, you're really multiplying everything inside here by -1, or you simply just change the signs. So for example, 4x squared becomes -4x, and positive 2x becomes -2x, and -3 becomes +3. All right? Then what we do is what's called collecting like terms. So we take a look at all of our x squareds. I've underlined them in green. Collect them. Okay? And when you collect them, you've got 2x squared minus 4x squared plus x squared gives you -x squared. And taking a look at our x terms, we have -7x minus 2x, which is -9x. Taking a look at our constant terms, they cancel each other out. -9 plus 9 gives you 0. So I just wrote in here that constants equal 0. So that's why it's not included. So that should be a review from last year. Something that we're going to add on here, which is called equivalent or equal functions or expressions. Okay? And the equivalency part is what's going to be new. Okay? Basically, there are two ways that you can find out how to decide if two functions are equivalent. Basically, you can simplify them to see if they become the same expression or the same function, or you could graph them to make sure they produce the same graph. Taking a look at example 2 here, ladies and gentlemen, it asks, are these two expressions equivalent? So what we're going to do is simplify the left part, and it becomes 6x minus 4b, and we simplify the right part in the blue. And in fact, what do we notice about those two? They have the same expression, so therefore these two functions are, in fact, equivalent. Looking at example 3, ladies and gentlemen, it's a little bit more different. You take a look at these expressions, and they're both simplified. Yes, they're in different order. However, we need to think about how do we interpret these, okay? First of all, looking at both those expressions, you should both notice that they are a quadratic function. They both have x squareds, and we're asking if they're equivalent. Well, we must decide, first of all, what form of the quadratic is the f at x and the g at x in? And they're in standard form, although they're in a different order, but they're still in standard form. What important information can you find out from that? You can find out the y-intercept, okay? So looking at the y-intercept for f at x, that would be -4, and the y-intercept for g at x is -11. So already there's one way we know that these are not going to be equivalent. The second part is to take a look at the shape of the graph, i.e. look at the a value. The step pattern has to be exactly the same. So a in f at x is 5, whereas a in g at x is -6. So there's another way we can tell that they're not equivalent. But to show or to prove that these are not equivalent, we just choose any value for x. You could choose 1, 0, -1, and show that f at a does not equal g at a. Just remember, ladies and gentlemen, if we're dealing with parent functions, x equal 1 is not a good solution or not a good substitution, because we know all parent functions except for the reciprocal ones have an equal point of 1 and 1. So let's take a look at these. We know these aren't these quadratics f at x and g at x. We know they're not parent functions because it's not simple. It's not just x squared. Okay, so let's sub in x equals 1. So f at 1, again, wherever you see an x, you replace it with a 1. So f at 1 equals 14. When we sub in x for 1 in g at x, we have g at 1 equals -14. So make sure you state here, ladies and gentlemen, that f at 1 does not equal g at 1. Therefore, f at x and g at x are not equivalent. Okay? If, however, folks, if g at 1 equals f at 1 or f at 1 equals g at 1, test for f at 2, g at 2, or f at 3 and g at 3 to see if they are equal. Simply because those parent functions tend to have similar points and still not be equivalent. Okay? And just remember, when you're done, if they are equal, then they are equivalent. Okay? So here is today's homework. It is page 88, numbers 2, 3, 6, 9, 11, 12, and 13. And again, some of those are challenge questions. Good luck with that. If we need to, we could do number 13 in class, because that is a tricky one. So just remind me, ladies and gentlemen, how to do number 13, or check my notebook. I've got the answers there for you. Okay? Have a great day.